Jnanam Paramam Dheyam. Knowledge is supreme.
In the last time we saw one example of a simple extension where minimal polynomial doesn't split into linear factors in the field L. So it is not Galois. Now I want to show an example of a field extension which the second condition can also fail. So that is I want a field extension L over K. So example, L over K I want and such that the degree is more than, this degree should be strictly bigger than the cardinality of the Galois group. I am writing such an example. So therefore L over K cannot be Galois. Alright, so it will not be, because it is not Galois, it will not be simple extension. Because we are going to prove soon the Galois extensions are simple extensions. So, and how do I give such examples? Of course, one easy way out is I want an example of a field extension whose degree is more than 1, but the Galois group is trivial. So, in other words, I want a rigid field extension. So the Galois group is minimal, that is only the identity trivial group identity element, and field extension has more degree. Alright, so take the base field K to be Z mod P and then rational function field in two variables K, U, V. U and V are indeterminates over K, and this is precisely the quotient field of the polynomial ring in two variables over Z mod P. This is my base field, and I am looking at the polynomial f. F is a polynomial in this field which has two factors, x power p minus u and x power p minus v. These are the two factors, and I am going to write what are the zeros of f. Zeros of f are precisely, there are only two zeros, u and v, with u power p equal to u and v power p equal to v. That is very easy to check. First of all, if u is a zero of this polynomial, where let us take an element u in the, so this polynomial is a polynomial with coefficients in k. So I definitely know there is a field L such which is field extension of k such that f splits into linear factors in Lx. This we know such a field exists because remember Kronecker theorem. Kronecker theorem says that given any polynomial f, we can enlarge a field so that all zeros of this f lies in this field, and I only take the field L which is obtained from K which is obtained from K by attaching the all zeros of F. So, in the notation also, one will write this L is K attached with all zeros of the polynomial F, and I know all the zeros, they are precisely U and V. There can't be any other zero, because if U is 1 0, that means U power P will be equal to U, and once U power P equal to 1, that means they are the zeros of U is a zero of this polynomial, and once U is a 0, small u is a 0, then x power P minus U, capital U is U power P, and this polynomial is nothing but x minus U small u power P, because P is the characteristic of the base field, which is positive. Therefore, once I know 1 0 of this polynomial, I know all the zeros of this polynomial. Similarly, once I know 1 0 of this polynomial, then I know all the zeros of this polynomial, and they are precisely U and V. So, therefore, there are only two zeros. What it shows is V of F equal to U comma V. So, there are two zeros. Alright, so what is the degree? First of all, the degree of the field extension is definitely more than 1. That is because U cannot belong to K, and V also cannot belong to K for the same reason. U cannot belong to K is very simple, because that is easy to check. So, I will just write here check. So, therefore, degree is definitely more than 1. Actually, it is not too difficult to prove that the degree is actually P square. So, I will also say here check. Degree is P square. On the other hand, what is the Galois group? Galois group I want to compute, and I want to show that Galois group of L over K is nothing but only the identity map of L. So, that is because, remember the most important observation of the Galois theory, which says that if U is a 0 of a polynomial, then and any sigma is any automorphism of L over K, then sigma of that is also 0 of the same polynomial. So, therefore, I want to apply that to this F. So, U is a 0 of F, and if sigma is any automorphism, then sigma U is also 0 of F. But sigma U is actually more than that. Sigma U is a 0 of the minimal polynomial of not only this, but V of minimal polynomial of U. But minimal polynomial of U is nothing but x power P minus U. This is a minimal polynomial. The F is not a minimal polynomial. This is the minimal polynomial of U over K. So, therefore, and the only 0 is U. So, therefore, we have no choice but sigma U has to be U. Similarly, V is a 0 of this polynomial F, and minimal polynomial of V is x power P minus V. So, therefore, that forces sigma V is also equal to V. That means every automorphism of the field extension L over K maps U and V to themselves. But remember, the sigma is uniquely determined by its values on U and V. So, sigma E is uniquely determined by this pair, which is U comma V. So, therefore, you have no choice, sigma U has to be identity. So, this proves that the Galois group is only identity. So, that implies sigma has to be identity on L. So, that proves our assertion. So, this extension cannot be Galois extension. In this case, what fails is the fact that there are no automorphisms at all of the non-trivial field extension. So, this can also happen, but this happens in characteristic P. We will come back to this in a more detailed way once we have enough vocabulary connected to the Galois group and a field extension. So, now the next goal is to prove that the Galois extensions are simple. So I will write a goal here. So L over K finite extension, finite Galois extension. Then I want to prove this is our goal. L is simple over K. Or that means that is L has a primitive element. Element over K. That means L is generated as a K algebra by one element. This is also round bracket because we are algebraic extension. So I will also keep saying L is a cyclic K algebra. That means as an algebra over K, it is generated by one element. That is what we want to prove. Alright, and what will be our machinery? Remember, whenever you have a field extension, L over K, finite field extension, then we have a group attached to that, namely the Galois group. And this is a finite group. And this group obviously acts in a natural way. This operates on L. So, and it operates on L means given any element x in L, I have two things attached to that, namely the orbit of x, those are the g multiples of x, and the isotropy gx. This is a subgroup of G, G in G. This, let us call this group as G. G in G such that G of x is x. I would prefer to denote elements of G as sigma tau etc. So that means this is precisely all those fixed points of the x is a fixed point of everybody. That means sigma of x is x for all sigma x. So these are the two objects attached to that, and we know the relation between them also, the cardinality of the orbit, that is very important. So I will just write that because we will soon use it. We know this was Lagrange. It says cardinality of the orbit equal to the index of the stabilizer. Index of the stabilizer is precisely the number of left cosets of Gx in G or number of right cosets of Gx in G. Both these numbers are same for arbitrary subgroup of a arbitrary group. So this is what I want to use it. So let me state a theorem now. So theorem, this is what we will prove. And as a consequence, we will prove that the Galois extensions are simple. So, L over K Galois extension. And G is the Galois group. Okay. And let us take Y arbitrary element of L. We want to prove at least one Y there so that L is generated as a K algebra by that Y. So I want to write down what is the degree of Ky over K and when will it be equal to the degree of L over K. In that case they will be equal. So note that Ky is contained in L and it contains K. And we are hoping that we can choose Y so that its equality holds here. That is our aim. And that can happen only when the degree of L over K equal to degree of this over this. This degree I know. The degree of this extension, we know it is degree of the minimal polynomial of Y. So I want to choose Y so that degree of L over K equal to degree of mu Y. This is what our aim. So I am interested in finding out what is the minimal polynomial in terms of course, the group. Okay, so what do I say? So I will write down formulas. So mu of y, minimal polynomial of y is nothing but, look at the product, x minus z, where z belongs to the orbit of y. Now I want to prove this. This is not obvious because this side is where is this polynomial? A priori this polynomial is in L. The coefficients are in L because z's are where? Z's are in the orbit of y. So they are apparently in Lx. This polynomial is in Lx. But to show that this equality, I have to show that this polynomial equal to mu y. To show this, I have to show first that the coefficients are in k, and not only that, this is a minimal polynomial also I have to say. This polynomial is of the least degree polynomial, and y is a 0, that is obvious because y is an element of the orbit. Every element belongs to its orbit. So 0 is obvious. Now I have to show that two important things, the degree, coefficients are in k, and it is a minimal polynomial. That means it's a minimal of the smallest degree polynomial. These two things I have to show. So this is an assertion 1. 2. Now chi of y. So let me remind you that, so this is remembering from linear algebra. So I will write it, recall from linear algebra. What do I want to recall? So whenever I have a vector space V is a k vector space, and a linear operator on V, F, V to V, k linear operator, k linear map. So it is an element F belongs to end kV. That means it's an endomorphism as a k, not k algebra. K algebra doesn't make sense. It's a k linear map. That is this. And now to this we have attached two polynomials. One is the characteristic polynomial of f, and the other is the minimal polynomial of f. Minimal polynomial of f is the monic polynomial of the smallest degree, so that mu f, when I substitute x equal to f, it is a 0 operator. Similarly, so what is the characteristic polynomial? Characteristic polynomial is defined by using the determinants, and the characteristic polynomial makes sense when this vector space has finite dimension. So we are assuming that it's a finite dimensional vector space. And what is the characteristic polynomial? You look at determinant of X identity matrix minus that matrix A, where this A is a matrix, it's a n cross n matrix, where n is this dimension, and the entries of this matrix are precisely Aij, and these entries are determined by, this is with matrix of F with respect to some fixed basis V. How are they defined? Just for the sake of recall, so they are defined by using the matrix F and the basis V. V has precisely n elements because the dimension of V is n. So let us take this fixed basis, and Aij's are determined by, for every j from 1 to n, f of Vj. This is an element of V, so this is can be written uniquely as Aij Vi. I is from 1 to n. So these equations gives you entries of this matrix. And if I take determinant of this, that means the diagonal entries x minus ai and off diagonal are the negatives of the original, then this determinant doesn't depend on the basis, and therefore this determinant is a polynomial. It's a monic polynomial of degree n with coefficients in k, because these aij's are elements of k. So this polynomial chi f looks like x power n plus a1 x power n minus 1 and so on plus an, where a1 to an are elements in k. So that means this polynomial is in kx. And Cayley-Hamilton theorem says that chi f, if I put x equal to f, then chi f is 0. This is precisely Cayley-Hamilton theorem. And because this mu f is a minimal polynomial with the property that mu f on f is 0, that shows that mu f divides chi f. So this divides chi f in kx. So I will write on the next page. So this is very important. So what we noted that mu f divides chi f in kx. This follows from two facts, the Cayley-Hamilton and the definition of the minimal polynomial. But this is not good enough for our purpose. So there is a more finer, this definition, this divides is a crude observation. So I want to make it more precise. So moreover, and that is very important for us, moreover, look at chi f. This may or may not be prime polynomial in kx. So this will definitely has a prime factorization, and I am going to write a prime factorization of this in kx. So that is pi 1 power alpha 1 pi r power alpha r, where pi 1 to pi r are distinct monic prime polynomials in kx, and they occur with the multiplicities alpha 1 to alpha r, and they are non-zero natural numbers. Actually, when I say prime polynomials, they are monic by definition, so I need not write monic again. So that is the prime factorization of chi f. If I write prime factorization of mu f, that will also look like pi 1 beta 1 pi r beta r, where the same pi i's and beta 1 to beta r beta i's, they are smaller or equal to alpha i's. There is no wonder, because mu f divides chi f. But what is more important is beta i's are bigger or equal to 1. So that means what? That means mu f and chi f have the same prime factors in kx. This is very, very important statement. In other words, there is whatever prime factor appears in chi, that should also appear in mu. And converse is obvious, because if a prime factor appears in mu, it has to appear in chi f. But more important, prime factors of mu also, prime factors of chi also appears in mu definitely with a non-zero exponent. Now I am going to use this statement. So now come back to our situation. Our situation was this. I have to prove the mu I is this, and I want to now write down what is chi y. So chi y is chi y should have degree how much? Now the vector space I am considering is L over K. Vector space I am considering is L over K. So that means I have to know what is the dimension of L over K, and dimension of L over K is precisely the degree. So remember, L over K degree is precisely the dimension of L over K. And let us call this as n. So that means this chi y should be polynomial of degree, monic polynomial of degree n. But n, because we are assuming it's a Galois extension, this n is also equal to the order of the Galois group. So that is the order of G that we know. This is because L over K is Galois. That is the definition of Galois extension. So therefore chi y should have degree equal to order of G. So this chi y I claim it is equal to product sigma in G x minus sigma y. Remember, sigma y's are elements of the group. The sigma is an element in the group. So how many elements are there? There are precisely n elements. And I am looking at these linear factors and multiplying them. So therefore definitely chi y has degree n. So this is obvious. So chi y is monic is also obvious, and degree of chi y is also n. That is also obvious. What is not obvious is the coefficients are in K. That is one thing. So this is our second claim. The third one is now the question is, I know I want to use the fact that chi y and mu y have the same prime factors. So chi y and mu y. First of all, note that mu y is prime polynomial already. It's a monic polynomial of the field extension, because what do we know? We know that kx mod ideal generated by mu y, this is actually isomorphic to ky, and ky is a subfield of L. So therefore this residue algebra is definitely a field. That means mu I generates a non-zero prime ideal. Therefore in particular mu I has to be the prime element. Therefore mu I is a prime element. So therefore there is no other prime factor. So if I have to write the prime factorization of chi y, what will it be? That will be chi y, and there is no other prime factor. So only which can happen is the power can occur. Now I want to write down that power, and that will be the observation 3. So that power is nothing but cardinality of the isotropy. This is isotropy, this is suffix y. So that is the third assertion. Once I know this, then I can, the fourth, now I just have to write down what is the degree of, so fourth, what is the, we are interested in the degree of this extension, ky over k. This extension degree is precisely degree of mu I. But degree of mu I will read it from 1. That degree of mu I is nothing but cardinality of the orbit of y. But cardinality of the orbit is precisely the index of the stabilizer. So when can this degree be equal to the, see we are interested in when can this be equal to L over k. Because I am interested in knowing when it is L over k, because if I have this, then L will be equal to ky. When can this be equal to, and this I know it is n, which is order of the group. So when can this order of G, and when can the isotropy will be equal? When this subgroup has to be trivial. So therefore this equality holds, that is the assertion 4. This equality holds if and only if the isotropy at y is the trivial subgroup. So that means if I have to prove that the given given Galois extension is simple, I have to find an element y so that the isotropy at y is the trivial isotropy group. Okay. With this, I will stop and we will continue the proofs of these 1, 2, 3, 4. Actually, 4 there is nothing. 4 I have indicated how to prove 4 because this was the only non-trivial fact there. The others was just trivial. So, I have to prove 1, 2, 3 and 3 also I have proved because I know the prime factorization of mu and therefore, I will know prime factorization of chi. I only have to find the power and therefore, that is also clear because the degree mu is the orbit, the cardinality of the orbit and therefore, degree of chi will be equal to order g and I have to supply this correct power. So, really I have to prove only 1 and 2 and which we will prove in the next lecture.